So we can expand this two-particle restricted Hartree Fock over a wave function. As 1 over square root 2 psi 1, electron 1, psi 1, electron 2. The two electrons are occupying the same molecular orbital, times the spin part, alpha 1, beta 2 minus beta 1, alpha 2, right? So one spin up and one spin down. They occupy the same molecular orbital 1, which is the highest molecular orbital. The highest occupied molecular orbital, or HOMO. And the second molecular orbital is the lowest unoccupied molecular orbital, right? LUMO. So essentially for this system, you only have two molecular orbital, and this is HOMO, the highest occupied molecular orbital, and this is LUMO, the lowest unoccupied molecular orbital. Okay. Right. Then let's look at the spatial part. What is the spatial part? Well, the spatial part is just psi 1 R1 times psi 1 R2. Now, psi 1 is the first molecular orbital, right? So the first term, psi 1 R1, means electron 1 is in molecular orbital 1. Psi 1 R2 means electron 2 is in molecular orbital 1. Right? So this is proportional to what? What is psi 1 in terms of the atomic orbital basis? This is chi1 R1 plus chi2 R1, right? Times chi1 R2 plus chi2 R2, right? This is the first molecular orbital, right? Here, this 1 means the first atomic orbital, right? This is the atomic orbital of the first proton, or hydrogen A. This chi2 is the atomic orbital of the second proton, which is hydrogen B, right? So from the first line to the second line is nothing but I essentially write the molecular orbital in terms of the linear combination of the atomic orbital basis, right? Okay, and then you can do a product, right? And this is equal to chi1 R1, chi1 R2 plus chi1 R1, chi2 R2 plus chi2 R1, chi1 R2 plus chi2 R1, chi2 R2, right? You have 4 terms. Okay. You just do the product, right? You have chi1, chi1. You have chi1, chi2, right? And then you have chi2, chi1, right? And the last term is chi2, chi2. Okay. So you really have 4 terms. Now, let's look at the physical picture. So this is the spatial part of the restricted Hartree-Fock wave function in terms of the atomic orbital. So what does this first term mean physically? It means R1, the first electron, is on the first atomic orbital. R2, the second electron, is also on the first atomic orbital, right? That means the physical picture is I have 2 electrons on proton A. I don't have any electron on proton B, and therefore you have hydrogen anion and a proton. Similarly, the fourth term means all the electrons, R1, R2, are on the second proton. Right? What is the second term? The second term means the first electron is on hydrogen A. The second electron is on hydrogen B. Okay, so you have first electron on hydrogen A and the second electron on hydrogen B. What is the third term? The third term tells you the first electron is on hydrogen 2. The second electron is on hydrogen 1, right? So you see, what is the physical picture about the restricted Hartree-Fock wave function? You will see the covalent, which means each hydrogen contributes 1 electron, right? And ionic, which means one of the hydrogen contributes 2 electrons, or H plus, H minus, right? You will see both the covalent term and ionic terms occur with equal weight. Right? So if you remember general chemistry, people like to draw the resonance structure. So those are the 4 resonance structure. Those are the 4 limiting resonance structure. You have 2 covalent structure and 2 ionic structures, right? But usually in general chemistry, we don't draw the ionic resonance structure, but it's there in the restricted Hartree-Fock wave function, right? You see, at the equilibrium, because the separation between these 2 protons is small, and essentially you will get a good description for the equilibrium geometry, for the equilibrium hydrogen molecule, right? But when you stretch the hydrogen-hydrogen bond distance, when you consider the dissociation limit, that is, the separation between these 2 protons is infinitely large. And of course, the overlap integral goes to 0, that's for sure, right? So the restricted Hartree-Fock wave function, which is a 2-particle wave function, is really 1/2 H minus H plus 1/2 the covalent structure, each hydrogen donates 1 electron, plus 1/2 another covalent structure. This time, electron 1 is on hydrogen 2 and electron 2 is on hydrogen 1, plus another ionic contribution, hydrogen plus, hydrogen minus. Then times the spin part, 1/√2 alpha 1 beta 2 spin up spin down minus beta 1 alpha 2, right? Of course, here you have 1/2. These are the coefficients in front of the atomic orbitals, right? It comes from the AO coefficient. If you go back to the very beginning of this lecture, we have the AO coefficient here, right? For the first orbital and for the second molecular orbital. And because when you go to infinity, the S12 goes to 0. And therefore, you only have 1/√2 here, right? Okay. And of course, 1/√2 times 1/√2, you will get 1/2. right? Okay. And what does that mean? That means we have 50% contribution from the covalent structure, which means you have two separated hydrogen atoms. And as the separation goes to infinity, this gives you 2 times the energy of the hydrogen atom. But remember, in the restricted Hartree-Fock wave function, we also have 50% contribution from the ionic structure with 1 proton and 1 hydride. And therefore, when the distance goes to infinity, the energy of a proton is 0, of course. There's no electron, so the purely electronic energy for a proton is 0. But then for the other part, you have the energy of a hydride, right? And based on superposition principle, we know the overall energy for the Hartree-Fock, for the restricted Hartree-Fock, at the dissociation limit is going to be 50% times 2 times E hydrogen plus 50% times E hydride, right? And this gives you the energy of hydrogen plus 1/2 energy of hydride. And of course, the energy of hydrogen is not equal to the energy of hydride, right? Notice that what is the energy of hydride? Based on variational principle, we have a product of the AOs, right? So you will have chi1 R1 for the first electron times, well, you really have chi1 times chi1, right? But for the second electron, you have normalization here. Plus, similarly, for the second electron, the kinetic energy of this second electron minus the attractive potential. And for the first electron, you have normalization, right? And don't forget, you have this product R1, R2, right? You only have, here you only have 1 hydrogen, right? One center. So really it's the product form for the first electron and the second electron, but they all have chi1 as their basis, atomic orbital basis, right? You have the repulsion between R1 and R2, the repulsion between the first and second electron. Chi1, R1, chi1, R2, right? This is the energy expression for hydride, right? Two electrons, but 1 proton. This is the energy expression, right? And the trial function, of course, is chi1 R1 times chi1 R2. Okay. And therefore, the energy of hydride is equal to 2 times the energy of hydrogen plus J11, right? This term is the definition of J11, right? 2 electrons on the same atom, right? And they are essentially, this is the repulsive interaction between these 2 electrons, right? This is J11. And therefore, the restricted Hartree-Fock energy at infinity is 2 hydrogen plus 1/2 J11. This is exactly the same as we derived from the previous section, right? If you follow the analytical expression for the restricted Hartree-Fock energy, you will get the same answer when you let RAB goes to infinity. But here, based on the spatial function, based on the physical picture, we know that this spurious term, this very strange term, comes from the ionic contribution. Right? So the restricted Hartree-Fock wave function contains too much ionic contributions. Too much. And that's why at the dissociation limit, you cannot get the energy of two isolated hydrogen atoms. You have 50-50 contribution from the covalent structure and ionic structure. It's too much. Well, you will say, okay, if you look at this restricted Hartree-Fock wave function, this is a spatial part, immediately you will say, I have one way, I have another way to improve this. Meaning you just simply, remove the ionic contribution. So we can consider another kind of trial function. And this is the so-called Hatteler-London valence bond wave function. This is not molecular orbital theory. This is valence bond theory, which means if you look at the restricted Hartree-Fock, which is MO theory, this is molecular orbital theory. If you look at the restricted Hartree-Fock spatial function, the spatial part of the wave function, you will have equal contribution from the ionic terms and covalent term. And those covalent terms are actually, they can lead to the correct dissociation limit, right? So in the valence bond method, which is abbreviated as VB, the spatial part is simply the covalent term. Right? So if you write these two terms in terms of the atomic orbital, then this is basically chi1 R1, chi2 R2, plus chi2 R1, chi1 R2. Right? Historically, this is exactly the wave function, the trial function that Hatteler and London used for treating the hydrogen molecule. So this is also the so-called Hatteler-London VB function, valence bond wave function. Of course, it will have a spin part, spin up and spin down. That's for the ground state. But here we just consider the spatial part. So historically, when Hatteler and London treat the quantum mechanics of hydrogen molecule, they use this spatial function, which completely ignores the ionic contribution. Right? This is what they do, okay? And this will lead to, of course, correct dissociation limit. Of hydrogen molecule. It will give you 2 separated hydrogen atoms, and that's correct. However, the deficiency is that without ionic terms, the energy of the hydrogen molecule at the equilibrium distance is too high. You indeed need one of the limiting resonance structures. Or you can say you need all of the limiting resonance structures. Because there is some probability of finding both electrons near the same nucleus, with one spin up and one spin down. So naturally, what is a better trial wave function? A better trial wave function will include the ionic covalent resonance. Your wave function should be a superposition of both the ionic terms and covalent terms. So Pythagorean should be, here I'm still writing the spatial part. Chi1 R1, Chi2 R2, plus Chi2 R1, Chi1 R2. This is the covalent terms, right? This is a covalent term because one electron is on AO1, another is on AO2. Or the first electron is on atomic orbital 2, and the second electron is on atomic orbital 1. So these two terms are covalent terms, plus lambda times chi1 R1, chi2 R1, chi1 R2, plus chi2 R1, chi2 R2. So here lambda is a variational parameter. You should do the whole calculation with this variational parameter and minimize this lambda, right? You should minimize the system energy with respect to this lambda. And this part means, okay, both R1 and R2, both the first and second electron are on this the first atom. Or both electrons are on the second atomic orbital, right? So you mix in some, but not 50-50. You mix some ionic terms into your overall wave function, right? So this will be a better wave function. So if lambda is equal to 0, then psi 0 goes to the Hatteler-London VB wave function. If lambda is equal to 1, then psi 0 goes to restricted Hartree-Fock wave function, which is the molecular orbital theory. Right? So as you see, in the Hatteler-London VB treatment, they emphasize on pairing two electrons together. Right? This is the conventional way when chemists think about the chemical bond. Two electrons, one bond. Right? This is the typical covalent picture. But if you really do the covalent picture without considering the ionic terms, the energy will be too high. Right? You have to mix in some ionic terms in your overall wave function, and that will give you better result. So here we have essentially two different kinds of theory. They are all approximate theory. Okay, we're trying to find the approximate solution to the original eigenvalue problem, and we're using linear variational principle. And actually, you can use nonlinear variational principle. So in valence bound theory, what we do is we choose, the first thing is still choose atomic orbitals, right? And then we put electrons in atomic orbitals. And we need to consider all of the resonance structures. You need to generate all the resonance structures, right? Which allows exchange of electrons in atomic orbitals, right? For instance, take H2 molecule under minimal basis as an example. What do we do here in the Heteler-London VB wave function is that, well, the first electron can be on atom A. It can also be on atom B. But if electron 1 is on atom A, then electron 2 must be on atom B. If electron 1 is on atom B, then electron 2 must be on atom A. Right? So you only consider the covalent terms. But this is just, historically, this is just the Heteler-London wavy wave function. Actually, in modern wavy function, in the modern wavy wave function, we consider all the resonance structures. You have to generate all the resonance structures in order to construct the VB wave function. And actually, you can further consider the atomic orbitals be further optimized. You can insert the variational parameters into the atomic orbitals, and you do this energy minimization with respect to all the variational parameters to get the best energy, to get the best solution or best approximation to the exact solution. This is the valence band theory, okay? This is based on the concept of the resonance structure and the pairing electrons. On the other hand, you have molecular orbital theory, which is Hartree-Fock theory. The first step is still choose atomic orbitals as your basis function. But the second step is you do a linear combination of atomic orbitals to form molecular orbitals. Right? And molecular orbitals are single particle orbitals. Right? You are only considering an effective single particle potential. This is the essence of Hartree-Fock theory. Particles are moving independently, right? And for each particle, it's moving under an effective average, the Hartree-Fock potential. Next thing you do is you put electrons on the molecular orbitals, right? It's really the molecular orbital is for the motion of the single electron over the whole space, over the whole molecule. It's not just between two atoms, right? This is the essence of molecular orbital theory. And then you construct the Hartree-Fock wave function, which is a Slater determinant, right? This is molecular orbital theory. This is what you do. Of course, you can further improve the accuracy of molecular orbital theory by including more and more basis functions and by including more and more configurations. If you consider a linear combination of multiple configurations, essentially you will get full configuration interaction with the complete basis set. And this is exact result, okay? So you should mix in the excited state Slater determinant in your wave function. Your wave function will be a linear combination of the ground state determinant, singly excited determinant, doubly excited determinant, etc. And you optimize the coefficient in front of those determinants. Okay, this part is no longer molecular orbital theory. This part is called configuration interaction theory, which is an improvement over the molecular orbital theory. And the best set of the molecular orbital is determined by solving the Fock equation, by solving the Rolfan equation in terms of the matrix form.